So we will see the system calls that are available in QNX OS in order to maintain or work with processes and threads. So first is process creation. How to create a process? So it is very simple. Either you can call, it is done in two steps, calling fork and exec, or simply a single function call called POSIX spawn. So any operating system has POSIX compliance, and so is QNX. So there are POSIX functions available which is indicated through POSIX calls, are like POSIX underscore followed by the system call. So here we have both the kernel calls, the system calls, as well as the POSIX calls. So fork and exec are the function. It is a two-step process. So either it is fork plus exec or simply POSIX spawn. These are the two options available for process creation. So fork, what it does, it simply creates a copy of the calling process. So obviously the program itself is a process which you will be writing, and from within a program only a fork or exec or a POSIX spawn can be called. So what fork does is it simply creates a copy of whatever program, like the process that you are working with, or the current process. A copy of it is created in fork. And in exec, a load program, it is basically a load program step where from storage some new process, new program is loaded to the earlier created process. So fork is for process creation and exec is to load a program from storage into the new process that we will be creating using fork. On the contrary, either it is a two-step process, fork plus exec, or a single-step process called POSIX spawn. So what is this POSIX spawn is, it basically does step 1 and step 2 together on a single call. So POSIX spawn or simply spawn is fork plus exec, that is creating a process and loading a program to it. Then there is this process termination. So there are three cases of process termination. Number one is detecting the termination of a child. Now, if there is this parent-child relationship existing between two processes A and B, then the death of a process is described in POSIX. How the detection of a death of a child is done is obviously true here also in QNX. And then we have this client-server relationship between two processes, wherein one process is terminated and how, say supposedly, server dies, how the client is notified, how the system is getting to know the death of a process. Then there is this last thing called the death pulse, which is kind of a signal that is making the entire system aware about the death of a process. So these are the three cases which we will study through process termination. So termination of a child, the first case. So when a child dies. So when a child dies, there is a parent and there is a child. The parent will be sent a signal called the sick child, and the sick child actually what it does is it does not terminate the process, and the parent will be sent a sick child when a process dies. And what the parent should do? So suppose there are two processes, process A, process B. Process B is the child process, process A is the parent process. If process B dies, the child process dies, it sends a sick child to the parent. And the sick child, after receiving the sick child, Now, receiving the sick child alone does not terminate the child process. What the parent should do is, it should wait on the child process. It should call the wait system call, that is wait or wait PID. You can see wait or wait PID system call in order for the process to child process to actually die. So simply receiving a sick child from a child is not termination. Only if the parent calls a wait followed by the sick child, it is the actual termination. And if a parent does not wait on the child, after receiving a sick child, if the parent process doesn't actually call wait, then what will happen? The child actually turns into a zombie. Now, what is a zombie? Zombie is basically a dead process. However, a zombie does not use the CPU, and the most of the resources it used are freed. Whenever the sick child is called, the process is died, right? So, most of the processes are, most of the resources are freed, but still, when you go and see the process manager, you can see the process being present. The particular PID of, like I said, every process has a PID. The PID of the dead process will be still seen if it is left out as a zombie. That is, if the parent doesn't call wait, if the parent process doesn't call wait, then the child process, it will remain as a zombie. It can be still seen in the process manager. Say for example, in your Windows system, what we do, we call the task manager, right? Control Alt Delete will bring up the task manager, wherein we can see all the running process, right? So similarly in QNX we have such a feature where we can see all the running processes. So the child that is sent the sick child, but the parent has not called the wait, then the particular child will be still present in the list of processes. However, all the resources or most of the resources of the process will be freed, and it still remains, only the ID remains. So such a process is called a zombie. Okay. So now what is the signal? Now the signal, the sick child or the signal that is in the parent, it will prevent the notification or the creation of zombies basically. So this signal sick child comma sick IGN, like if this is called, then it will prevent the notification of death and creation of a zombie. So we will see a hands-on example towards the end of the video. Now we will just walk through all the methods or the termination of different cases of termination of a process. So the next case is the process termination, that is when there is a client-server relationship, how the death of a process is notified. So if you have a client-server relationship, like I said, two processes, process A and process B, can exist in a client-server relationship. So if a server can get notification, basically the server will be notified if any of its client dies, and a client will get a notification if any of its server is dying or any server dies. So this is done, or this is applied through QNX message passing. So these notifications will happen on death of a process, but they can still happen otherwise as well, because a client and server process is meant to send and communicate messages between them. So this communication between the client and server obviously happens all the time, but very specifically through message passing, the death of a client process can be notified to the server, or the death of a server process can be notified to the client. So this is the idea of letting the termination of one process known to the other process, that is maintaining a client-server relationship in a QNX system. It is done through message passing. Now we will see in the future lectures, maybe we will see what is message passing in much detail. So what is a death pulse lastly? So now this is the third case which we saw. So you may ask the OS, typically I have say hundreds of processes that is being alive, and if a particular process dies, the OS can actually deliver a notification. We can make the operating system, I mean the kernel, to raise a notification as soon as any process that is existing in its user space dies. So there is a register to notify function. You can see proc manager event notify. So when this is done, when this call is made, we can actually get a notification when a process dies. And you can see the request should be very specific with this variable being configured, that is proc manager event process death notification. Now this should be configured in order to get a notification of a process death in the user space of a QNX kernel. And the notification can be anything. So this is the event that is being delivered for this function call can be anything. It can be signal event, or it can be a pulse event, or even it can be a message passing, or like anything. So mostly a pulse is preferred. Like a pulse is a single very short communication without any overhead. So a pulse is typically preferred for indicating process deaths in a QNX system. Now that's it about the idea of process, what is a thread, how a process is created, and how it is terminated. Following this, we will see a very short hands-on demo wherein we will create a process, we will kill it, and we will see we will see the existence of a zombie process as well. We will see a very short demo.
Hello and welcome you all to the hands-on session on the QNX Momentics IDE. So what is QNX Momentics IDE? So it is an integrated development environment which is used for developing, compiling and debugging and executing applications for the QNX Neutrino real-time operating system. So it is an Eclipse-based IDE which has provision for code editing, project development, and to maintain a target connection, and process monitoring and debugging as well is possible in this IDE. So this IDE supports several platforms out of which x86 and ARM are very popular. It also supports a Raspberry Pi environment. Since it is having support for ARM Cortex, it is also supporting a Raspberry Pi hardware. So the developers basically use C or C++ as a language for creating their application. And this IDE also has support for automating the build process using a makefile based automation. So here in real time, we can analyze the system behavior of the running processes with the help of this Momentics IDE. So before starting with the experiment, so the first step is through the installation process, which is very neatly documented in their website. So the first step, I can just quickly walk you through the installation steps. The first step is actually installing the QNX Software Center and then going for installing the two important packages QNX 800 and QNX Momentics IDE. In addition to this, I have installed the software development environment for the x86 architecture as well as the ARM architecture, so that I can run my applications on any Raspberry Pi hardware, or I can also use a virtual machine. So this is about the IDE. So since I have my packages installed, I just go for launching it. So it takes a couple of minutes to get launched. So I have created my workspace, wherein by choosing it as the default workspace, I'm launching the IDE. So this is version 8.0.3. So this is the Momentics user interface, where we have a project explorer, editing space, and a console, which is put together. And the project explorer also shows the target devices. So here I have configured two virtual machines, VM1, VM2. However, we can also connect to any hardware target to this IDE. So we will quickly go through creating a project. So the project creation is pretty simple. So it is file, new, QNX project, and in that go for choosing a QNX executable, C++, QNX executable. Next, I should give a project name. For example, I will give first PRJ, which means first project. Then I have to choose the CPU variant where I will be running this project. So I have decided to run it on a virtual machine. So I will go for choosing x86 as my CPU. Finish. So once I created the project, we can see in the project explorer, we get to see this first project, which is having all the separate organized folder for the binaries, the executables, the source files, etc. So the first project.c is the source file, which actually turns out to be here. Okay, so now I will demonstrate the first experiment, wherein the experiment gets a string, some sort of string like this as input from the command line, and print the same for every iteration of this for loop on the console. So the first step is to write the C file, that is first prj.c, with the necessary main function, and then the next step is to write the make file. So make file is basically the commands for automating the build process. So since I am planning to run it on a virtual machine, so I am enabling this target to be the x86 architecture. If it is another hardware like Raspberry Pi, I would go for uncommenting this second line here and commenting out the target as x86. What this build process is all about is creating an object file and then the binary file for the corresponding C file which we have written. So this is a very simple make file. So the compiler we are going to use is QCC, and yes, we have the debug option enabled. So with this, I have written a very simple make file. Always press Ctrl S to save any changes that you do to the file. Then once you make any change to the make file, please clean the project once before building. So I clean the project, then I go for building the project. So once I build the project, now you can see this binary file generated for the first PRJ project, which is suitable to run in a x86 architecture. So for this, what I do, I start one of my virtual machines in order to run this binary. It takes a couple of minutes to start the virtual machine. Okay, once my VM1 process is done, we can see here my virtual machine booting with the QNX SDP, that is the boot image of the QNX. Now after the virtual machine boots, this state here would change to a connected state. Let's wait until then. Yes, now we could see my VM1 is the connected target and it is ready for running any application. So I am going to right click this binary file and run as application configuration. Since I have to give some command line input, I go for running it as application configuration. If there are no command line arguments need to be given, you can directly run it like simply press the play button over here. So now I go for the arguments and I will type in something like this, say hello, says QNX or something like anything you like, some sort of string, and go for running. So here we can see this is the whatever message we gave in the console is being printed here continuously for every iteration of this for loop here. Since it is placed inside a while loop, while of one loop, for every iteration of this for loop, I can see my message being printed. Okay, so now since the program is or the main process is running, I will just to stop it from running, I will use this stop button. So this is the first experiment where we have got a command line argument and printed the same in the console. So in the next experiment, we will see the creation of process and termination of processes in this Momentics IDE. To demonstrate processes, we go for creating a new project like we did earlier. File, new QNX project. In that, we go for a QNX executable. Project name, I give something like process demo, and I'm going to use a virtual machine again. So there is this process demo project folder being created. Inside the project folder, there is a source folder with a C file in the same name as process demo and a make file. So we need to edit these two files. Okay, so here we have put the program for demonstration and into the .c file, and also written the make file corresponding to the process demo.c file to generate the object file corresponding to the source file of this project. And as the usual practice, we save so whenever you have this issue like the project explorer closing or the screen being switched to something like this, you can go for perspective, reset perspective, in order to bring all the console and explorer into the window. So here we can see the process demo.c and the make file are ready now. So the first step as usual is to clean and then go for building. Yes, and we could generate the binary file for the demo. Before seeing into the program, we will see how the particular program works. So basically, these are the steps. The first step is a child is created using POSIX spawn. The child simply sleeps for 30 seconds and it terminates. So during this 30-second period, the child can be visualized using a PIDIN command. Later, when the child dies, it terminates with a sick child signal. But still, if you go for calling a PIDIN, you can visualize the zombie. Now that is again a 30-second sleep period where you can call PIDIN and visualize a zombie. After this 30 seconds, the parent process now calls the wait function. As a result, the zombie is cleaned up, and at this point, if a PIDIN is once again called, there will be no zombie process or no process with the child's PID can be seen. So this is a simple demonstration of creating a process, a child process, terminating it, and visualizing at each step of the process. Okay, so now we see the program in much detail. So we include all the necessary header files that is needed for process creation, signal handling, input output functions, error handling, and process related operations. Following by that, there is a function called sigfunc which is being defined. So this function is a dummy signal handler, and this is just to attach a handler to the sick child function, that is the sick child signal which is given whenever a child dies. So this is just a dummy handler. Following by that is the main function. So the main function is initially we set the stage for the described process. We declare all the necessary variables like PID, child status, SET and RET. Then these are steps for simply emptying the signal set and then configuring sick child as one of the signal to the signal set. And this is a pthread sigmask. Now this function is called in order to just unmask for the process to the sick child function. I mean sick child signal. So we add the sick child signal to the signals, and this is basically setting up the stage for the process. After this, the PID of the parent is printed using the get PID function. Next, we set the attributes for the child, which are like what is the sleep period, and then go for creating a child using POSIX spawn. So if this POSIX spawn, in case it failed, we print a error message. If a child is created successfully, then the PID of the child is printed. After this, we can visualize the child process through its PID in any one of this method, either by calling a PIDIN or by looking into the target navigator. Now, the parent process waits for the sick child signal, and the child continues sleeping for 30 seconds. Once the sleep finishes, the child terminates and a sick child is generated. So we know this. So then when the child generates the sick child signal, it has died, and PIDIN should show now it as a zombie, and we print this message. And in order to have some room for visualization, we sleep for 30 seconds. Followed by that, the parent process now waits on the child by calling the wait function. And this wait function call actually collects the child's termination information, and this also kind of removes the zombie process that earlier existed. So we can now, towards the end, we can see the output that the zombie is now gone and the child process died with the following status, with status 0. So towards the end, we have another 30-second sleep period for observation. So this is the idea of the program. Now, when I run this on the virtual machine, so you can see the child is working for some time and then it is dying. So to visualize this, we have to go to Window, Show View, Target Navigator and expand this VM1. So we can see the zombie process existing. Now, since the child has died, first 30 seconds has passed. Now, once the zombie is dead, we can see the target navigator, the zombie being released. So this is the execution. So in this lecture, we have seen how a process is created and how a process death is notified through sync child and how a dead process exists as a zombie and a zombie is cleaned up. In the next lecture, we will see how threads are created and destroyed just like processes, and we will also uncover some programming examples for systems with multiple processes and inter-process communications. Thank you.